So anyone know what pairing-based cryptography is? No? You, maybe? Who here knows what Affinity is? A company that just raised $100 million. Anyone heard of this project? Yep, okay. What makes Affinity so fascinating, so interesting, is that they have a thing that allows them to dynamically elect a leader for who gets to mine the next block in such a way that it is deterministic, meaning we all can come to the same answer, random, meaning it can't be predicted in advance, and it's ungameable, meaning that I can't try to sway it. And it's also Byzantine fault tolerant. This is a really amazing subset of characteristics for what is effectively a decentralized random number generator. And how they do this is based on two pieces of core technology that we're going to kind of walk through here in 1 second. One is BLS Signatures, or Bowman-Lynn-Shockham Signatures. Short signatures is the other thing they're called, as well as Shamir secret sharing. And we'll kind of dissect what these are. This is part of the reason I was really hurrying through the front half, is most of that stuff I was talking about, you guys are probably already familiar with as blockchain devs and developers in general who've messed around with crypto. This is the stuff that most of you probably haven't messed with much because it's pretty new. What pairing-based cryptography does, though, and this is what's kind of on the screen, is we talked about earlier the DH key exchange. It allowed two participants to come to a common shared secret in such a way that no one else in the world could know what that was. Pairing-based cryptography allows the same thing to occur for 3 participants. It's still not considered secure under the original protocol that was devised in, I think it was 2002 to do so. But out of this set of characteristics, we also inherit the ability to construct things like zero-knowledge proofs, and a lot of the really fancy fun stuff that we're getting used to dealing with today. And so what you see here is E is what we call the pairing function, but you'll notice from the construction that goes on, you see we've got 2 curves, G1 and G2. G2, G1, at least within the library that I've implemented, you'll see that. And you'll see that we have B, C, and A. The nice thing here, these are our private keys that are in the numerator. And then G to the B is our public key. As we were kind of talking about earlier, that's that multiplication. What's interesting here is that it doesn't matter in which order we construct this pairing operation. It's commutative under multiplication and addition, meaning that you can see I've got G to the B, G to the A, all equals the same thing, ABC, 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 and it doesn't matter whether it's A or B or C or whichever one of these subterms. This is that really nice property that allows the use of pairing-based cryptography to do things that are otherwise not possible in normal crypto. And basically what it's actually doing underneath the hood is we're doing what's called a mapping or transformation space. I move from one space and I do a transformation and I end up in a destination space. So this is linear algebra, if any of you have ever done linear transforms. It's the same fundamental idea. I'll let you guys kind of look into what the background of that is without getting really mathy and boring. But what gets awesome about this is we can do things like BLS signatures. And I could have gone into zero-knowledge proofs, but this is already heavy enough, and I've basically just been throwing information at you. So without going down that rabbit hole and just throwing even worse information at you, I thought I would just go to BLS signatures. BLS signatures are short signatures. They're the thing that allows the deterministic randomness I was talking about from Affinity. The reason why is they don't have that K hiding factor that I was droning on about earlier inside of it. They basically do some black magic where I essentially get to just take the signature as the hash times the private key, and then the public key is the private key times G, same as before, right? And we do this cool thing called hashing to the curve. But what it allows me to do is to get rid of that K factor. And since I don't have that random K, it means that the output is deterministic. The same signature is always the same signature for whoever's signing. And because it's deterministic, what this allows is, if I use the next topic, which we're going to talk about, is Shamir secret sharing, to split up a key between a group of people so that it takes multiple parties coordinating in order to sign a piece of information. I can have a group of you try to sign a message so that no matter what subset of you sign that message, so long as there's enough of the, what we call the threshold level of you signing the data together, I will always get the same signature. But none of you could have figured out what that signature should have been in advance, hence ungameable, and it's random. We don't know what it's going to be, but it is deterministic. We can all come to an agreement of it. So basically, if we're talking about BLS signatures and Affinity, what we're doing is we're creating a threshold level of people that must sign a piece of information as the Byzantine level of consensus. And once everyone has co-signed this piece of information, we get that random value that's always the exact same no matter what subset signed it. That was a mouthful. Here's actually the code that allows you to kind of see how BLS signatures work under the hood and to go play with this. And this is really, really fun crypto because you can do a lot of stuff here that are not possible otherwise. So this was constructed from two sources. One, from the PyECC backend libraries, two from the Ethereum Research Foundation, because writing this hash to curve function is really, really hard. So I didn't want to spend all day yesterday trying to rederive that from research papers that I barely understand, so I just used theirs. But this code works, it generates a valid BLS signature, and allows you to kind of play with what's going on underneath the hood. The process here is that I take a message, and I can't just hash the message and then take the output. In this scheme, what I actually have to do is I have to recursively hash a message until the hash of that message creates a valid point inside of the curved space. And we can think of this almost as like generating a public key for which we do not know the private key. And this is what makes BLS signatures secure, is this hash to curve operation. If you didn't do this, it actually destroys the underlying security of trying to do these types of operations. But once we've hashed into a curve space, you can look up what I'm talking about there, running out of time, then we can go in and use the pairing operations. And so you'll see the first pairing, we calculate the signature itself here as the hash times R, which is our private key. This creates S. This is literally the signature, and it's just the same multiplication we've been doing all along to derive public keys from private keys. And then we have our verification. So R up here is our public key, little r is our private key. We have the pairing S and G1. That allows us to check on one side, and then if we run the second algorithm, C2, that's actually how we get a verification of a BLS or short signature. Effectively, if you trace out the mathematics, this is done even in the Wikipedia page, so I'm not going to put it up on the screen, but if you look at how this works, what's effectively going on underneath the hood is the sets of operations where it doesn't matter if it's G to the A, and then G to the B inside the parentheses, or you move those A's and those B's around to different locations, it all just works out the same, no matter what. This is the property that's allowing this to kind of occur underneath the hood. So, once again, running out of time, I know I've been flying through this and I apologize. Go look up what I'm talking about, but here's an existing Python implementation that lets you play with it. Okay, the last thing I'm going to talk about is this Shamir secret sharing protocol. Shamir secret sharing lets me take a key and I can divide it up amongst, say, everyone in this room so that it would take some arbitrary subset of you in order to rederive the key. This means that I can create true multi-signature systems where it takes multiple parties to generate a single valid signature. The implementation that's used here is insecure because it leaks the private key when you try to recover it. This is the most trivial implementation of Shamir secret sharing that I'm about to show you. And it came from a company called Blockstack. I ended up having to clean up their libraries because they didn't work in Python 3. In the appendix of this presentation is those cleaned up libraries, so you can play with this also without having to go back and do the same work that I did. But what's going on underneath the hood here is we take a secret and we fraction it into a polynomial. Basically, if any of you remember b plus or minus the square root of 4ac over, whatever, it's what allows you to solve second order polynomial functions. If we take a polynomial and we make a complex equation of order 5 or greater, we basically can't solve the math behind this thing. And so what that allows us to do is we can give you all effectively one of the zeros or the factors of this really big polynomial we build, and then some subset of you can come together and zero out the function and get back the primary secret. The more advanced forms of this technology allow a group of you to negotiate a polynomial in such a way that it has no central authority who's doing it, and you can generate signatures without leaking the private key. The best implementation of this technology that I'm aware of today is actually through the parity Ethereum client under a thing called the secret store. So if you're not familiar with what the secret store is, you should go look it up. It is groundbreaking, cutting-edge technology. It allows you to have encrypted smart contracts. It allows you to negotiate multi-party signing so that there's no single point failure for pieces of data, and allows you to negotiate multi-party non-single point failure encryption using Shamir secret sharing and all of the other things we've kind of been talking about. This is the libraries that I was talking about. If you want to see how all of this kind of stitches together, go look at the Blockstack GitHub that was listed at the very top up here. You'll see how it all kind of sources out, but that's where I was fixing all the bugs. That's in the appendix. That was a lot for me to just throw on the table, and I sincerely apologize to brain dump on all of you this way, but it was too much information for me to do anything else other than attempt to show you some code and let you figure it out for yourself. I can't teach you guys all of this, there's just too much. I can give you some tools that allow you to go break it and then put it back together and figure out what does work and what doesn't work. So please, I'm going to put back the very first slide, which carries the link. Or no, it's actually on this slide also. Please, if you want to play with all this code, it's in here. It all runs on Python 3. All the dependencies are listed. I've removed almost all the dependencies back to the core libraries. So go play with it, have fun, break it. You can build cool stuff. Don't use it in production unless you really know what you're doing. Don't roll your own crypto, right?